Hi, I'm Zeynep. So yeah, this is a work, I mean, it's an extended abstract about this comprehensible ASP reasoning by means of abstraction, like how abstraction can be used. And it's based on the work that I did for my PhD, like where we introduced this abstraction notion. So I will immediately begin with ASP. So answer set programming, it's a knowledge representation and reasoning paradigm. It's widely used in problem solving, and thanks to its non-monotonic semantics and the expressive power, it's quite, there are many application areas for it, and there are quite efficient solvers out there, which makes application of ASP through many different areas of AI very easy, including planning, diagnosis, and also common sense reasoning. So yeah, I think that's why this ASP is a convenient tool for investigating ways of applying human-inspired problem-solving methods. And just to give a more tiny background, so ASP answer set programs consist of rules of this form, where you have this positive body and you have the negative body and you have the rule head. And yeah, for example, to describe the graph coloring problem, which is the problem of, you shouldn't color two nodes that have the same age. You shouldn't color them the same color. So this would be the general graph coloring problem. And you can elegantly describe it with set programming, where you first describe your instance with these facts, where you give your graph, like you have these colors, you have these nodes, and you describe which edges you have. And then the idea is to first guess a coloring for a node, and then check whether this coloring indeed satisfies certain properties you want to achieve. So all nodes should be colored. Yeah, a node shouldn't be colored more than one color. And if two nodes have an edge together, it shouldn't be colored the same color. So it can be quite easily described. And the semantics relies on this notion of stable models introduced by Gelfand and Lifshitz. And for this instance, for example, these answer sets, the models that you get for this program would give a coloring for this instance. And if you give another instance, a graph instance, which is actually not colorable, then you would get no answer sets. So there have been many works that have been constructed for ASP, and which can also be used for comprehensible ASP. So there are works which are more theoretical, that talks about simplifications of programs, where they studied having more simplified programs that preserves the same properties as the origin program. And there is ongoing work about verifying ASP programs, where you verify whether this program satisfies certain properties. And of course, there are works about getting explanations, like you get justifications of why an atom occurs in an answer set, or you debug if a program does not have an answer set, or whether some answer set does not occur. So you can use such debugging methods. And there's a nice recent survey about that. But also mentioned in the survey, so the obtained explanations you may get may contain too many details, which prevent one from seeing the crucial parts. So overall, some notion of abstraction can come in quite handy for ASP, for getting more comprehensible ASP. So the notion of abstraction is not new, of course, in KR, because it's about focusing on key details, disregarding the rest, and it's been agreed that abstraction plays a key role in representing knowledge and reasoning. And the idea of creating an abstract space, solving the problem in the abstract space, and then guiding the search for an original solution in the original space has been used many years ago. And this idea is especially being used in planning, where they make use of abstraction to compute heuristics. And there's also this notion of hierarchical planning. Again, you have abstract actions and then you decompose them to more concrete actions. And also some desired properties for abstraction has been investigated. And also for robotics, more ASP-related languages has been used where they also consider different abstraction layers to find plans. And usually in these works, the abstract representations are constructed by the researchers themselves. So they think about the abstract representation and the concrete representation and continue from there. So the abstraction notion that we introduced for ASP is about constructing an over-approximation of a given program through either omitting atoms from the vocabulary or clustering the elements of the domain. And the idea is to automatically find an abstraction that gives you concrete solutions. And for that, we made use of a CIGAR-inspired methodology, which I will talk a bit later, where you start with the highly coarse abstraction and then you refine it until you get an abstraction that gives you concrete solutions. And we implemented them in some tools and applied them to several benchmarks. And in the end, we realized that the resulting abstractions that we get can be used actually to get an understanding of the problem at hand. So this is what I will talk about here. So since I have quite a lot of time, I will first give a bit of background of this abstraction notion ASP, and then I will talk about what its potential in comprehensibility, and then I will conclude. So the idea of abstraction is about over-approximating the problem into a smaller and simpler state space by deliberately losing information. And this idea has been used especially in model checking, where they describe models through transition systems. And from a given original transition system, they want to construct an abstract transition system and ensure that all original transitions are preserved in the abstract model. And this way, this abstract system can simulate the original system. However, since you do such an over-approximation, you may get spurious transitions here. And for that, you may need to refine the abstraction to get a bit more coarser transition system where you may get better results. And for that, there's this method of counterexample guided abstraction refinement introduced by Clark et al. And there the idea is as follows. So you start with the highly coarse abstract system. And then there you want to check whether for all paths certain property holds. And you get a counterexample where it does not hold. And now you need to check whether indeed this counterexample occurs in the original transition system. If not, then it is spurious. Then you use some ideas of, you check the spuriousness and you get an idea of how to refine this abstraction. And then you refine it. And this continues until you either get a validation that the property holds on all paths, or you get a concrete counterexample. So this was the idea that we use for answer set programs. So we called an answer set program pi prime to be an abstraction of pi if you have a mapping between their vocabulary, and the vocabulary of pi prime is smaller than pi, and you want to ensure that all original answer sets can be mapped to some answer set of the abstract program. So in this abstract program, the size of the answer sets could be smaller, but since this is an over-approximation, spurious abstract answer sets may exist that cannot be mapped back. But if this abstract program has no spurious answer sets, it's also possible, then we would call this abstraction faithful. And this is a useful property to have, which I will mention later. And furthermore, thanks to this over-approximation, we know that if we have an abstract answer set which has abstract program which has no answer sets, then we can immediately conclude that the original program also doesn't have an answer set. And this is again a useful property which I will show later. So again, with the graph coloring problem, where we have this non-tricolorable graph, if we omit certain nodes it will still remain uncolorable due to this click here. And for this graph, which is actually possible to color, these nodes are distinct nodes, and they can just be clustered together, and they can just be colored anything. So this again, and these two abstraction notions were the ones that we considered. So the first one was omission abstraction, where we omit atoms, and domain abstraction is about clustering the atoms. And in our works, we showed how for a given input program, SSF program, for a given mapping, how to construct an abstract program which satisfies this over approximation. But since how to find a good mapping is tricky by itself, we have this whole methodology of finding an abstraction. And the idea is similar to this SAGAR I mentioned. So you start with the program and a mapping which is very coarse, like you cluster all the elements together, or you omit everything, and you construct the abstract program, and then you check whether it has an answer set. If yes, you get the answers, and then you check whether it's spurious. If it is not spurious, then you're done. You have an abstract program, the mapping, and the non-spurious answer set. But if it is spurious, then you refine the mapping, construct a new abstract program, and continue. And this continues until either you reach a program which doesn't have an answer set, or you find a non-spurious solution, and this continues until you reach the original program. So for this graph coloring, you omit all the atoms, or maybe just leave one, or you cluster all the nodes together. And with this, you get some spurious solutions, like here, it thinks it's colorable, and here it finds a color that colors everything to blue. And then you refine until you either realize the uncolorability, or you find a solution which is non-spurious. So we had this whole methodology, and we implemented it in some tools. And we realized that these outputs that we get, these mapping that we get, actually shows some key elements of the program, which also can be used for comprehensibility. And this is what I will mention now. So as humans, we use abstraction quite without knowing it actually. And we have this abstract thinking where we remove irrelevant details and we identify the essence of the problem. And there are many works on seeing how humans think using abstraction. And there's also this work of Johnson Laird, which talks about mental models. And usually the approach we take when we tackle large and complex structures is to determine the relevance among objects, or determine the relevance of the program, like the most relevant part of the program, or we try to distinguish some common properties among the objects so that we have a bit more high-level view. And these two things can also be achieved with this abstraction notion that we have. So first, removing irrelevant details. So as I showed before, this omission can be used to omit the parts which are not relevant for the unsatisfiability. So we have this origin graph, we start with the initial mapping, and then we get this final mapping, which shows the uncolorability. And we say that these atoms that we keep in the program and omit the rest are called to be blocker sets, satisfiability blockers. If we keep them and omit the rest, we still have an abstract program which is unsatisfiable. And the subset minimal blocker sets would then be the most relevant part of the unsatisfiable program. We also applied it to a planning problem, this 15 puzzle, where you have this initial state and you want to arrange the tiles to this form, where we start with this initial mapping of just omitting all the numbers of the tiles. And then we find a mapping which was saying that it's unsolvable within 10 steps. And it shows that indeed, these 4 tiles cannot be arranged to this form in 10 steps. And we also recently applied this notion to explaining non-acceptability and of arguments in abstract argumentation in this recent ECI paper. So relevancy is also can be found for solvable problems, so not just unsolvable problems. And for that, we made use of domain abstraction where we clustered elements and we applied it to some scheduling problems. And where this idea is you have certain tasks and they have certain slots and they need to be arranged in certain time, within certain time points. And when you start with this very coarse abstraction of clustering all the time points into one, you get eventually a mapping where you construct a scheduling which is not spurious, and it actually helps you distinguish these key time slots in scheduling. And we then took a bit more specific route where we focused on multidimensional domain abstraction, where the idea was to achieve a hierarchical abstraction over the domain for zooming in. And we especially wanted to focus on grid cell problems where the zooming in effect is easily visible. And then the idea was to see whether this automatically obtained abstractions that we get in the end, they can match the intuition behind the human explanation to unsolvability. And for that, we did a small user study with some students here from TU, where we gave them two sets of problems. One was the reachability problem, where not every cell was reachable from the starting point. And for that, we asked them to mark the area which shows the reason for having unreachable cells. And we would expect them to mark some obstacles with showing that there are unreachable cells. And we also gave them some instances from Visitall, which is the problem of finding a path that visits every cell once and visits all the cells. But if you have two dead-end cells, for example, you cannot find such a plan here. Or if you have like these single-way passages, again, it's not every cell will be visitable. And then we asked them to mark the area, which shows the reason for not finding a solution that visits all the cells. And these were the exact sentences that we gave them. And so we gathered the results from the users, and then we ran our tool to automatically find an abstraction that realized the unsatisfiability of the program. And we were happy to see that we indeed, the tool indeed had the ability to zoom in to the part where the users are also focusing on, like to show the obstacles. And this was also found by the tool as well. And for the Visitall, like the two dead-end solution, two dead-end cells, we found that the tool was also able to zoom into that part to realize that it's unsolvable. But we also found out that the tool had to zoom in a bit further, like to see these parts to realize unsolvability. So there was a bit different layers of abstraction. Like here, it was enough for the user to mark the two cells, but for that, the tool itself had to zoom in a bit more to realize it's in a grid cell environment and some properties does not hold, etc. And interestingly, we also had some unexpected input from the user, and this was quite interesting. So we had some users that marked the unreachable cells themselves, like not the obstacles, but the unreachable cells, and some were marking just one of the dead-end cells and the obstacle next to them. And then this showed that indeed this meaning of explanation, like finding the reason, showing the reason, is indeed very different from people to people. So we also had some not so good results, like different results. So again, this is reachability, where the user marked this area to show not every cell is reachable, while the tool was always automatically finding these parts, like these parts to show that it's unsolvable. So it's still true, but it's not the same that the user was focusing on. And here for the single way passages, the tool was focusing on very different parts. It was just focusing on all these cells that could be reached from the single passage. And then it was able to realize the unsolvability. And then this, yeah, because it also depends on the encodings that you use to describe your problem. So we realized that it's indeed maybe quite different than what we expect. And we again had some unexpected user input where some people were just marking some obstacles to show the reason, or they were marking some cells that was reachable through single way passages. But yeah, these were quite interesting results, and I would really be interested to pursue these further. And yeah, there's also this generalization that I wanted to talk about, and it's about distinguishing the common properties. So I showed that for this graph coloring, we can start with a general clustering, and then where we have spurious colorings, and then we can find a mapping of just clusters, these nodes, and then we no longer have spurious colorings. And actually these programs are called, these abstractions are called faithful because there are no spurious colorings, and such faithful abstractions can be used to reason at the abstract level by distinguishing these common properties of the clustered elements. So we also applied it to some planning problems where we consider this notion of multi-table blocks world problem, where you have this initial state and you want to pile these blocks to this table, and it doesn't, yeah, and this is the initial state. And actually, then what we did was we clustered all the tables and then looked which abstraction that the tool found. And the tool was finding this abstraction where it doesn't need to distinguish these tables, and it only needs to distinguish the table where the blocks need to be piled up. And this was already enough to find a faithful abstraction. So any plan that you find here can be applied in the original program. And this shows that indeed these tables within this cluster are not really of relevance. And they have this common property. And we also applied it to this package delivery problem where we had these packages here and we need to deliver them here while passing through these checkpoints. And then at first we clustered all the locations, and then we automatically found the mapping, which only clusters the checkpoint location. And then this shows that it doesn't really matter through which checkpoint you pass, and whatever whatever plan you find here can be applied here. And of course, this brings the notion of generalized planning, and the relation to it would be something interesting to investigate. So that's it. So we have this abstraction notion, which shows potential in finding the essence of the problem solving, which can be useful for human comprehensibility. So we have this automated way of starting with the initial abstraction and achieving an abstraction with a concrete answer. And this automated way demonstrates a human-like focus to the key elements in the problem. And it can be used as a guide to decide on good abstractions for reasoning. Of course, there are many challenges remain. So one of them, like the most important one, is finding ways to make use of such abstractions to help the users in understanding the decision-making behavior. So far we have these mappings at hand, but how do you show these to the users so that they understand the problem? Do you make use of justifications or visualizations, or it's still unclear? And of course, there's also this challenge of achieving the various levels of abstractions that humans use with respect to what the machine needs. And this is also something interesting to compare. So that would be it. Thank you.